So we have the local force vector, the local displacement, and the local stiffness. That's quite easy to set up. If we just write here element A first, then we will have F is equal to, so I have the element here, then I have F3, F2, and these are all in direction X, and then you have F2Y and F3Y. So that the force vector is written as then F3X, F3Y, F2X, F2Y. Then you have the displacement, which will be written exactly in the same way. You have U3X, U3Y, U2X, U2Y. And the stiffness is also going to be the same. You will have, let's calculate K equivalent, which is given as 70 e to the power 3, area is given as 10, and the length of this particular element, which was horizontal, is given as 125. So the stiffness for the first element is 5.6 10 to the power 3 Newton per millimeter. So we will use this value, so you will have 5.6. I'm going to put the e to the power 3 outside, or you can actually put all of it outside. Then you have minus 5.60. Well, you know exactly how this works by now, but I'm just working it out for completeness, and there's enough time so you can work alongside of me. So that's the stiffness matrix, the element stiffness matrix for A. So I should write here KAE. Yeah, that makes it much more clear. Now we know that the displacement vector, so the displacement of the node 3 here is actually equal to 0. So that means these two terms will become 0. And we also know that it's fixed at 3 because U is 0. These two terms will become reaction forces. We also know that F2y is given to us. So F2y will be equal to minus 100 kilonewton, which is because it's acting in the downward direction right here. So we can also substitute the value here. So the unknown here is now F2x, which we cannot define yet because we don't know the value. Of course, there's no load applied here, so we can call it 0. There's nothing. U2x, U2y are the unknowns, which are going to be found out later. So in the same way, we are going to set up now the element B. Now element A was not oriented in any particular angle, it was just 0, so we don't need a transformation matrix. So in general, we can write KA element UA element is equal to FA element. Now that can be easily written, so I can write here A. Then let's get on to element B, which is rather interesting and new case for us, so I will go slow. Free body diagram again. I want to make the this is element sorry, that was completely wrong. It is at an angle. This angle is theta, which we already calculated. We know this is node 1, this is node 2. Then you have all the forces and the displacements in the two directions. So I'm not going to write them out here, but rather I will write them out here. So I have FB for the element will be given as F1x, F1y, F2x, F2y. And please note that these are the local coordinates x and y. Then you have UB of the element, which will be given as same U1x, U1y, U2x, U2y. Then we can set up the stiffness matrix. So you can also write this here. I'm not going to do a final one. I'll just write KE is equal to K equivalent. And K equivalent in this case is 70 e to the power 3 into 10 divided by, we had calculated this number before, which was given as 160.08. And if I calculate this, I should get a value of 4.37 e to the power 3 Newton per millimeter. So I can just put it in here. I will say e to the power 3 outside. 4.37, 0 minus 4.37, 0. 4 times 0 minus 4.37, 0, 4.37, 0, and again 4 times 0. Now, the interesting part, the transformation matrix, because this is just a local one. That's quite nice, but we need to do a transformation of this matrix to get to the global system. So we can write here, this is for the local one. Let me just write it like this. So you have FB E is equal to KBE UBE. Now let's also put some boundary conditions before I move on to the transformation matrix. So I know that it's fixed at u1x and u1y, so these would become 0. Then there is no then you do not, so these are basically also going to become reaction forces, but only in the global coordinate system, not directly here. And you will have F2y in the global coordinate system will equal to minus 100 kilonewton, and F2x would be equal to 0. So this is already established before. U2x, U2y as before are the two unknowns. Now let's set up the transformation matrix. We already have the relation for the transformation matrix, so it's nothing fancy. The transformation matrix will be given as, I'm just going to copy it from the previous derivation, cos theta minus sine theta 0, 0, sine theta cos theta 0, 0, 0, 0 cos theta sine theta, 0, 0 sine theta, sorry, this is minus and this is cos theta. Of course, this is only for a 2D plane. Please remember that. So now I know the value of theta. Theta is equal to 38.66 degrees. So I'm just going to substitute it in there, and I will have therefore the transformation matrix. Sorry about that. That went by fast. So I have my transformation matrix T, therefore, okay, now I know why that's happening. I keep pressing the cross instead of going forward. So I'm going to avoid doing that. Therefore, transformation matrix after substitution. And I hope you're also calculating this with me alongside. So if there are any errors in the numbers, please do let me know. So the transformation matrix for element B are given as 0.78087 minus 0.6247, 0, 0, 0.6247, 0.7808700, and exactly in the same way, I'm just going to fill it up very quickly. Is the transformation matrix. So all the components have in general been calculated. So if I want to make it into a global system, then I need to do a transformation of this system. So if I say I have KB of the element in the global coordinate system, if I would like to have it for the element itself, not a global stiffness matrix, because then I would have to superimpose two stiffness matrices, then I can write this as transformation matrix times K, P of element, and transformation inverse. If you calculate all of this, then you will be able to fit in numbers here. So you have e to the power 3 in the matrix, 2.67, 2.13, minus 2.67, minus 2.13, and so on. I'm going to fill in these numbers while I hope you also calculate them. You can of course pause the video here if you would like to make sure that you have enough time to set up the problem and get a solution to it. I'm almost done here. So now I have the stiffness matrix for the element B in the global coordinate system.